Welcome to Textile Update, the podcast where we can share our passion for textiles, fibers, and yarns. This is Gwendolyn Hustvedt.
This is the second and last podcast about how we manufacture fibers. So we've learned about chemical spinning, and now we're going to talk about some really common modifications that are done for many or most manufactured fibers. So we've extruded a fiber. Now what? Manufacturing fibers is very much a 20th century innovation based on what we learned about how silkworms extrude protein out of the orifices in their, well, not really face, but head somewhere. And so one of the really cool things about being in control of the manufacturing, right? The manu in manufacturing doesn't refer to mankind or humankind. It refers to man as in manual, right? So when the human hands made the fiber, not just the textile, but the fiber itself, we have a lot of control over how that fiber ends up being formed and what sort of properties it has. So we are extruding a fiber out of the spinneret in a process known as chemical spinning. That fiber is hardening, right? And the hardening may be either because it was hot and is now being exposed to cool air. It could be because it had a solvent in it, right? Like an acetone, and it's now being evaporated using warm air, right? Or because it's in a bath of chemicals that allow it to coagulate, sort of gelatinize into the shape of a fiber. But in every case, the fiber is at this moment larger, and the polymers inside of it are more disorganized than it ever will be in the future. So if you watch a YouTube video about fiber manufacturing, just Google fiber spinning or DuckDuckGo fiber spinning and find a video on Vimeo or somewhere else that shows you how fiber manufacturing happens. You'll see that basically the fiber comes out of the spinneret, and then the technician, the video I watched, the lady in the lab coat grabbed the fibers and then wound them around several rods. What was happening there is a step that's called drawing. We talked about drawing way back when we talked about fiber properties, and we talked about filament fibers. We talked about whether or not we could make a fiber more oriented or more crystalline, and at that point we learned that drawing was the process that could do that. So yes, in fact, we can take the fibers as they come out of the spinneret as soon as they're hard enough to handle, and we can begin to stretch them, and that stretching forces the polymers to become more aligned, puts them in close proximity with each other so that if they're interested in forming a crystal, they will do so, right? And so how much we draw, right, how far we go with this drawing depends on how much orientation we want, how much crystallinity we want. Remember that as the fiber is more oriented, it gets stronger and more abrasion resistance, but it loses its elongation and its absorbency. So if we're making a suitcase, we're going to really draw the heck out of those fibers. But if we're making a garment that's meant to absorb human sweat, then we're going to draw it less and accept that we end up with a fiber that's a bit less strong, right? So that's something that happens in almost every case, just as soon as a fiber is manufactured. But the extent to which it happens is guided by the end properties that we want in the fiber. Now, at that point, we have really long filaments, and we can either leave them as filaments and roll them around a big cone and ship them off to be immediately fabricated into a fiber, or we can cut them up into small pieces and make them into what's called tow. But I say immediately, but of course we'd almost never do that because we have so many choices of ways to modify the fiber that we're probably going to do a few other things first. So let's talk just a little bit about what else we might do with the fiber, the modifications. Now, first of all, we modify the fiber in a number of different ways. One of the ways that we can modify it is by changing the composition of the dope, the material, the liquefied materials. So we could melt the polyester chips, and then we could sprinkle in pigments to change its color. Or we could sprinkle in antimicrobial chemicals, right? That mean that maybe the material would have some antimicrobial properties. We could sprinkle in flame resistance chemicals or sun protective chemicals, right? And as I mentioned way back when we were talking about identifying a manufactured fiber under the microscope, we very often, in the case of rayon, sprinkle in basically pigments that are like sunscreen, right? Titanium dioxide or zinc oxide used as sunblock, right? In order to deluster the fiber, to make it less shiny. So the polymer that has had nothing added would be called the parent fiber. And then after that, we might have a second generation fiber or a third generation fiber where we could purchase a barrel of olefin chips that had already been tinted to a shade that we're interested in, or had already had sunscreen added, and sunblock. If it's titanium dioxide or zinc oxide, that would be sunblock. So we could purchase a second generation material instead of a first generation material. And the more modifications, then the more generations we would have. And I've just explained the very first type of modification, which is called solution additive. Now, the really cool thing about this is the most permanent way that we can add color to a textile material, right? The pigments, or in some cases the dyes that are sprinkled into the dope, are embedded inside the fiber. They are not on the surface. They didn't depend on chemical bonds, right, to form a relationship with the polymers inside the fiber. They're just trapped inside the fiber. They have no choice. It's permanent. It's a life sentence. And so the great thing about that is that people are never going to complain that the color washed out of your product. The downside of that is you're committing really, really early to what color the product will be. You do not have time to say, whoa, actually, coral wasn't as popular as we thought. Hold off, right? So very often the colors that are used in these first generation already colored materials are basics, right? So long-standing trends within interior design or garden design. Right, I was so excited when they finally did sort of a turquoisey color in plastic outdoor chairs, right? Because I didn't want a lime green chair or a mustard yellow chair. I wanted a turquoise chair or a geranium red chair as opposed to an orange one. And so recently those have trended in. I wanted them because trends come from our unspoken desires, and I'm a human being, and so they had detected my desire for a geranium or turquoise colored chair, and they started producing a lot of first generation polymers that had already been colored to be those colors. White is a real good old standby, right? Lots of times we'll just make it white. I've mentioned some of the finishing compounds that we could add, like UV resistance. We could also add things that improve the wrinkle resistance, for example, of a cellulosic fiber that might have trouble with wrinkling. So we could put the cross-linking agents right in the dope. We could put in an anti-static material if we were going to make the fiber into carpeting, right? But the most common things that we might add to the solution, to the dope, are colors of some sort, dyes, pigments. Another subtle category of those, because we don't actually see it, but they're there, are optical brighteners, or also known as fluorescent whitening agents. These are compounds that absorb ultraviolet light and then retransmit it very close to visible light. For this reason, they actually provide a bit of sun protection, because the ultraviolet light is what was going to destroy and damage our DNA. And instead, it just sort of gives it a very faint blue glow. You might have seen this under a black light, right? So that glow actually makes things appear whiter, because the glow is blue, and we don't know we're seeing that blue glow, but it cancels out any yellowing that might have been present in the material. right? And so these optical brighteners, turns out Americans in particular are really obsessed with whiteness, the white teeth. You can spot Americans in a crowd anywhere in the rest of the world the minute they smile, because first of all, they're a real smiley bunch, and secondly, because their teeth are practically glowing. In fact, in the Global Organic Textile Standard, there was in developing this totally international standard on how to produce textiles that could be labeled as organic. There was what the stakeholders referred to as the Walmart exception, which shows just how American this desire to have things be whiter than white is. I've got to say, it seems kind of like we're obsessed with whiteness, because in the standard they had a little carve out that would allow manufacturers producing for the U.S. market to use optical brighteners that were prohibited for the rest of the world, because the stakeholders just made the case that if they're not allowed to use whiteners, they will not be able to sell undyed products. And on balance, they said, well, you know what, not using the dye, it has an overall net environmental benefit compared to the very small harm that might be caused by the optical brighteners. Not harm to people. Optical brighteners don't hurt you in any way. You're probably putting them in your mouth when you brush your teeth anyway. So no, the optical brighteners are just there to make things have a subtle glow. Almost every laundry detergent has it in them, has them in it anyway. So that's an example of something that changes the color that we can't quite see. I mentioned the delustrants, titanium dioxide and zinc oxide, and then those absorb light, both UV and visible light, and so they actually both provide sun protection and make the fiber appear duller, right? Because you've got these tiny little black freckles that are like sucking in the light. So solution additives, first generation modifications, very common. Another incredibly common way that we modify manufactured fibers is by switching out the spinneret to change the shape or the size of the hole that the fiber is extruded out of, right? So nature sets the cross section for natural fibers depending on the goals that have evolved for what that fiber is doing. But we can just say, you know what? I don't think we want round fibers. I think today we want trilobal fibers, because we know that the trilobal cross section will be shinier and we want things to shine today. Or we might say, ooh, let's use this particular spinneret that actually produces fibers that have a hollow void in the center, which allow them to be a little bit stiffer for their bulk, right? So making them more lightweight, and yet that by hollowing them out, you have a larger overall diameter, right? And so you get the benefit of that, but that central hollow channel can help with wicking, because we now have two surfaces, the inside and the outside, that can both wick moisture, right? And so we could do that with the cross section. Some common cross sections are a dog bone shape, which provides more cover for the same amount of material. We could have a what might be called a striated shape, right? So it has lots and lots of little bumps on the surface and long grooves along the surface contour, basically kind of a jaggedy star-shaped hole. And so depending on our goals, in many cases we start by imitating the cross sections of natural fibers and seeing what happens. Our goal is to change the light reflection to make the surface of the fiber feel less smooth, in the case of the multilobal striated surface, to reduce crush resistance, like I mentioned with a hollow void, to improve insulating ability or wicking. Or in the case of the dog bone, to make it a bit loftier and a little bit bulkier. So that's something that we can really easily do, is change the shape of the hole in the spinneret. We can also change the size of the hole in the spinneret, and this leads us to a new discussion that we have to have, which is about how we size manufactured fibers. Natural fibers are sized they're sized based on the yarn that we use to produce out of them, right? So we don't just, well, we do say, for example, that, this particular fiber is smaller, but the sizing method that we use to denote that the fiber is smaller actually comes from measures we used for the yarn. So we have to go all the way to, we spun the yarn, and if the fiber was really fine and small, right, then the same weight of yarn would make, so if we weighed the yarn, but when we measured the length of it, it would be a lot longer, right, than if we weighed it. So what there was a time when yarn was spun as a, quote, cottage industry. So people spun the yarn from their own sheep at their own home, and a buyer came around and bought the yarn from you. And so you would have actually set a standard length, right, that you were reeling off, right? So maybe 100 times around a wheel, and this was the standard length of your skein of yarn. And then the buyer would weigh the standard skeins of yarn against a set weight, so like a big 5-pound weight. And you would keep stacking your skeins of yarn on the scale until you reached the standard weight. So if your yarn was very fine, you could make more skeins of yarn for the same amount of weight. So you might stack 80 skeins of yarn that were all the same set length on the scale, and they would say, ooh, that's 80s wool, right? Whereas if it was thicker, right, you would only be able to stack maybe 40 skeins of yarn on the scale before you reach the same weight, right? And so you would end up getting paid less because you'd be paid more if the wool was finer. And so this is an indirect method and results in the fiber being described as 80s or 40s or 120s or hundreds, right? Because it takes more skeins to reach the same weight. In the case of manufactured fibers, on the other hand, we don't have to go through that like extra step. We may not ever even spin it into yarn, and so we really need to be able to talk about its size immediately. Plus, we know the size of the spinneret hole, right? So we could just literally measure the fiber, right? But we still know that after we draw it, it'll get a little bit narrower. Some things change. It may be modified slightly. We have a weird cross section, like where do we measure from? The dog bone, like the widest side or the narrowest side. So we still need a way to actually talk about its weight and size. And so we use a term called denier, right, which is the weight in grams of 9,000 meters. So material that's made into, average apparel might have a denier between 2.5 and 7. Technically, it's 2.4 is the line. So between 2.5 and above is normal, and then 2.4 to 1 is considered fine. And then from 1 down, right? So 9,000 meters of the fiber weighs 1 gram. 9,000 meters, 1 gram or less. That's what microfiber is. Drives me nuts when I'm reading descriptions of products in online catalogs and it says, what is it made of? And the seller responds, microfiber, right? Microfiber is a description of the size, not the fiber content. Is it microfiber polyester, microfiber acrylic, microfiber, we don't make microfiber rayon, microfiber nylon, right? Microfiber is just a description, right? It's like saying, oh, is your baby a boy or a girl? And you say, it's tall. That doesn't answer the question, okay? You described it, but, and actually, you know what? Being tall may end up having more impact on it throughout its life, right? Height is important, but still, right? It doesn't answer the question. Ultra fibers are even finer. They are smaller than 0.3 denier. 9,000 meters of the fiber weighs less than a third of a gram. That is a very, very fine fiber. Microfibers are, as I've said, right, you can change the hole in the spinneret, but to get to less than a third of a gram for a fiber, which could be used for apparel, but more often would be used for very special industrial purposes, maybe medical purposes, we have to actually start to get more clever. So obviously when we draw the fiber, it gets narrower, so maybe we allow it to harden more slowly so that we can draw it even more, right? But that still may only get us down to microfiber. So we've had to come up with a few more ways to do it. One method, which is sometimes called the Sea Island method, not to be confused with Sea Island cotton, is where we extrude incompatible polymers together out the same spinneret hole. And then we crush it afterwards after it's hardened, and the fibers didn't really want to be together anyway. Maybe one was had been, as a second gen material that had been made to be hydrophilic, and the other one was hydrophobic. So they kind of ended up pushing each other apart. And so you can end up with basically like half a fiber or a third of a fiber, right? The Sea Island refers to extruding the one fiber into the center of the other one so that it becomes like an island in the sea of the other fiber. And then when you break it apart, the island can be recycled, and the sea, which would be the little tiny pieces that were all around the island that break off, are actually used as the microfiber. And then a third method, besides drawing it or using incompatible polymers, would be to just eat away at the surface of the fiber using a solvent that dissolves the fiber a bit, right? This is a little tricky. You have to be super careful. But actually, this process helped us discover ways to improve wicking, for example, because when we pit the surface of the fiber, we create little channels for moisture to wick through. So that's a major modification, size, right? So we can change the diameter, we can change the size. And then final modification, basically the fourth, we had solution additives, cross-section, diameter, and now the major modification that's very commonly done is called texturization. And this is because many fabulous natural fibers like wool have a 3D crimp. So we can actually crimp the fibers right after they're drawn, right? We just pass them through either a mechanical crimper, like a set of gears that may still be very, very slightly liquid, right? Still a tiny bit warm, right? And so we can crimp them using these gears to give them a crimped shape, right? We could use heat to crimp them, just like a crimping iron. We could draw them across the edge of a knife blade, right? You've curled ribbon for packages, right? You lay the ribbon on the surface of the blade of a scissor, press your finger against it, and then pull. What's happening there is the side of the ribbon that's against the knife blade starts to get hot, and so it contracts because it's heated up. The side that's touching your thumb, although you feel the heat, that side doesn't contract as much, and so it actually curls in on itself and creates this spiral, which is a way to get a 3D crimp. And so we would use many of these different crimping methods in order to imitate natural fibers for things like carpeting or batting, which would be used inside pillows or mattresses or quilting, to be used as inner lining, right, inside of a garment to make it warm, or just like this suit coat right here. It's polyester. It's one of the things I love about it because this suit coat will never die. It will never wear out. It will never fade. I will own it for the rest of my life, and it will be launderable, and yet it does feel like wool, right? So in the end, I can still tell, but it looks like wool, right? So so that is the wonderful opportunities that we have to actually modify manufactured fibers. So as much as I love natural fibers, I also really love all of the mechanical stuff and chemical stuff that we're able to do here. And that basically concludes our discussion of manufacturing fibers. We'll move now back to regenerated and synthetic fibers with this knowledge in mind, right? Knowing actually how the fibers are manufactured. And then I'll just say, oh, that was wet spun, or that was dry spun, or that was melt spun, and you'll know what I'm talking about at this point.